Hi again. In this video, we will explain why it is a good idea to upgrade from a basic path-based testing variant to constrained path-based testing, and also why this option might be, in certain situations, better than more advanced modeling notations, such as extended finite state machines or timed automata. As we said in the previous video, the simplicity of the basic path-based testing concept is both an advantage and a disadvantage. The advantage is that almost everyone is capable of understanding the system model and creating it. That may sound trivial, but it's an extremely important feature of the model. However, for certain cases, the model may be too simple, and when using it, we may not be able to handle certain real-life situations properly. We've talked about the semantic gap already. Because the basic model hinders some of the internal complexity of the system under test, some test paths may be unfeasible as a result. Take this simple example. We model a workflow as a directed graph, and on paper, everything looks fine. However, objects handled by the workflow have the natural character of a state machine. They simply change states as the workflow proceeds, and in certain situations, it may not be possible to continue with the test because some of the objects have changed state, so a test path becomes unfeasible. The information on there being some objects handled by the workflow and their changing states is not reflected in the model. This is exactly what makes the semantic gap. Apart from the semantic gap, other real-life situations also matter. It's common that some parts of the system may be expensive to test, or we may have limited resources for testing. Typically, this can happen in the Internet of Things systems. Some devices are battery-powered, and some functions in them can drain the battery fast. So we have a limited number of attempts to do a test. A similar effect may happen in field tests, when the team members doing certain parts of the tests with the hardware have limited time and energy. You might wonder, how does this affect my project? We don't do terrain field tests with first responders to test any specialized hardware equipment. Now, just think about a time when a part of your test environment had an outage that caused half of the testing team to stop working for a few hours. When did that happen? Yesterday? This is actually a very similar case. Part of the process becomes unavailable, and we need to react fast and select the tests that can be done to prevent 10 or 20 people from not being able to work for hours, which is a great waste of time and money we need to avoid. There are also countless other situations like this. Additionally, very frequently, the test manager simply decides, we have tested this part of the process enough, so in this test round, let's focus on the other parts more intensively. Similar to this issue, a general test prioritization is not possible. Naturally, we need to cover certain more important parts of the workflow with stronger tests than those that are not as important, so we need a mechanism to do this effectively. Finally, in some situations, we may need to not test certain parts of the workflow, because when we do that, the rest of the tests would not be possible. All these situations have one thing in common. In order to have a solution, we need to explicitly tell the test paths where in the workflow to go, where not to go, or where to go only a limited number of times. Just in a few defined places in the workflow, that would suffice. So, we need a model that would allow for this. The first idea that comes to mind is upgrading to a more complex and, therefore, more powerful model. In this video, we have selected two of them as examples: extended finite state machines and timed automata. Let's get to the basic idea behind them, just very briefly. Let's compare these models to the basic model we talked about in the previous video. The extended finite state machine actually serves to describe the parts of the system under test that have characteristics of a state machine. This is a slightly different thing from a workflow, but they are similar, and the basic mathematical structure behind the model is also the same. So it might be good for the case. At first glance, if you are not familiar with state machines, have a look at the link below this video. The extended finite state machine adds more things to just a basic directed graph that models the process or a state machine. We use update functions, enabling functions, and an internal memory. It even starts to resemble a very archaic, simple computer model. And it is possible to model the cases we had on the previous slide in it. The exact definition of extended finite state machine can be found by clicking on the link below. When the matter we need to test is strongly driven by time flow, by an internal clock, which is typical for electronic systems, we may choose a timed automaton to model it. So, an internal clock is a part of the model. Besides that, similar to the extended finite state machine, there are guarding conditions in the model that capture how the system works. Using a timed automaton, we can also solve part of the previous problems, but this option is a rather specialized thing for testing electronics. We show it here to present how diverse the models can be despite their similarity at the very first glance. Now, let's talk about the possible drawbacks of all three models that we have discussed. We have just described basic model simplicity and the drawbacks arising from it, which are, to recap, a semantic gap and the inability to handle a number of practical situations that occur during the real-life testing process. On the other hand, the extended finite state machine and other alternatives can handle these problems, but there are several issues. First, the creation and maintenance of such models is costly. However, they are a good fit for testing mission-critical systems, where the nature of the system under test corresponds to the structure of the model and if there is enough time and money to maintain such models. Second, if we model the managerial decisions related to the testing process, or we model resource and technical constraints via guarding conditions and transition rules in these models, it is technically possible, but we start mixing modeling of actual behavior of the system under test with these additional resource and managerial constraints. That is absolutely not what we want because it might lead to confusion and errors later in the model and test design. Third, the extended finite state machine and timed automata may not be the best fit to capture processes and workflows. These two things usually have different topological patterns compared with state machines. It's difficult to describe these patterns exactly or to give a formal mathematical definition. However, every test practitioner can intuitively tell the difference between a workflow to test and a state machine in most cases. When each one is converted to its core structure, that is, a directed graph, state machines usually have many more cycles and fewer end states. So, the flow may repeat in cycles, whereas in a workflow or a process, the flow usually goes from the start point to an end point, by a main flow or by taking a detour on the way. Of course, exceptions and counterexamples may be made, and we all know how discussing them is so very interesting. However, on average, in the majority of cases, the patterns are as we have just described. So, the question is there any option that would be just a bit more complex, hence expensive, compared to the basic path-based testing model, which can also handle the problems we have described? Finding such a model is actually what we are doing when defining and consolidating the constrained path-based testing. Now that we have understood what our motivation is, let's introduce the method in the next video.